Okay, hi everyone. I'm Michael Dinitz from Johns Hopkins. I'll be talking about new graph spanners in the greedy algorithm. So before I do that, I just want to thank the organizers for inviting me to give this talk. I love going to DISC. I love ADGA. It's too bad we can't all actually be together. But hopefully I'll see you all on the Zulip chat and in all the kind of other ways that the organizers have made this a surprisingly fun conference. Yeah. So I also want to say this is kind of a weird talk, maybe. So like I said, I want to thank the organizers for inviting me, but I don't really consider myself a distributed graph algorithms person. I've kind of, I think, skirted the rules a bit here because I write, a fair number of PodC and DISC papers, and I write a fair number of graph algorithms papers, and these kind of don't overlap a lot. So a lot of my PodC and DISC papers are about graph algorithms, but they're not really distributed. They're, compact routing, they're spanners, they're kind of other things that distributed people care a lot about. But I, have, with some exceptions, tended to focus more on centralized computation of them. A few small exceptions here and there that I'll talk about. But yeah, so, I had a couple papers that I had in mind that I could have given, honest to God distributed graph algorithms talks about. But I thought it would be maybe more interesting, especially if there's students in the audience, to kind of instead say some of the centralized stuff that I'm very excited about that hasn't yet made its way to the distributed community. Okay, so today is a talk about objects that distributed people care a lot about, in particular spanners, and some settings and some results in the centralized world that I think make probably even more sense in the distributed world. So in some sense, this is like a big advertisement for a bunch of open problems, saying, here's this recent progress we've made in centralized. Can we do something similar in distributed? And here's why, I think it's hard, but here's why I think we can do it. And I think it'd be really cool if we could port some of these results over to distributed land. Good. So hopefully by the end of this talk, everyone's going to kind of come out very excited and prove a bunch of results saying that all this stuff we were doing centralized, we can now just do distributed, and that would be awesome. I would be super psyched if you all managed to do that. Okay, so let's get started. This talk is about spanners, right? So probably a lot of you know what spanners are, but probably not everyone. So just to remind you, and to introduce the topic, we say that a subgraph H of G is a T-spanner if distances in H are at most T of what they are in G. Right? So distance is your normal shortest path distance. Note that because H is a subgraph, distances in H are at least what they are in G. And so that means that all distances are basically preserved up to this factor of T. Right? So it's a graph sparsifier that preserves distances. You can contrast this with graph sparsifiers that preserve cuts or preserve the spectrum or preserve any other property that we care about. Here it's distances. This factor T is called the stretch. Metric embeddings people sometimes call it the distortion. I tend to use stretch, but I might go back and forth. In this paper, or actually I should say in this talk, G is undirected and connected, right? So there's a bunch of interesting stuff we can say about directed spanners. We're not going to do that today. Connectivity is just kind of basic, right? Otherwise, I just do these things in each connected component. So we're going to assume connectedness. And an easy result, which we're not really going to use, but it's worth seeing as a warm-up, is that it's sufficient for the stretch condition to hold for all edges, right? So the definition is for all pairs of nodes, but really it's just for all edges. And you can kind of easily see this. This is because the stretch is multiplicative. And again, there's a whole super interesting line of work on non-multiplicative stretch. So additive or kind of combined multiplicative and additive or kind of even more complicated functions. And there you have to kind of be careful. There you have to do all pairs. But here we can just do edges. And that'll be useful in some of the algorithms. And this is also maybe an indication why in distributed land, this seems plausible, right? Like if I have some edge, I only have to consider things edge by edge and talk about short paths to replace edges. So this should be something I can do distributedly, intuitively. It's very local. So, a nice example, maybe I should also mention, there's a bunch of very nice pictures in this talk, and these were basically all made by my collaborators because I'm horrible at making these kinds of pictures and I have no design sense. So any kind of nice slide you see is due to my collaborators, and any kind of crappy slide you see is probably due to me. Just to kind of give credit where credit is due. So here's a very nice picture that I think Greg Bodwin made. One of my collaborators made this. Yeah, okay, cool. So you can see like I have this kind of dense original graph G that's kind of hard to look at and figure out what's going on. But I can kind of get this other graph H where the distances are about what they were. They're factor 3 bigger. And it's much sparser. It's easier to look at. Like it's kind of easier to reason about. It's just a nicer graph to be playing around with. Okay. So, one of the interesting things about spanners, right, is that definition that I just gave you is nothing about distributed, right? That definition is purely graph theoretic. So, these things could have been studied a long, long, long time ago, right? And yet they weren't, right? They grew out of this community. They grew out of the PODC, DISC, distributed algorithms community, distributed computing community. Right? So these are kind of the 3 papers that people usually cite as the kind of beginning of graph spanners. A PODC, a stock, and a journal of graph theory. So we've got the spectrum there. You can see David Peleg's on all of them. David is one of the people who invented these things. And ever since the 80s, the late 80s, there's just been enormous amounts of work on spanners in both centralized and distributed forms. So probably a lot of people watching this have worked on spanners, but it's a surprisingly big topic given how simple the definition is. Okay, so that's distributed people care about this. That's the point I'm going to make, right? That these are objects that are in some sense purely graph theoretic, and yet they're super important in distributed computing, and they're kind of the original motivation is from distributed computing. Okay, so like I said, the plan today is to kind of talk about these recent results that I'm very excited about on spanner variants in the centralized setting, where I don't know how to do the same thing in distributed land. And I'm going to talk about these 2 different settings because the reason is kind of the same. The reason is that the centralized results use a greedy algorithm. It's called the greedy spanner. And the greedy spanner is super nice. It's all these nice properties. It's been studied extensively. Is an awesome, awesome spanner. On the other hand, greedy results are tricky to do in distributed settings, right? If I'm trying to be greedy over a whole graph, like how do I do that when I have locality? How do I do that when I have congestion? Right? It's tricky. And so because of that, there's been just like a very cool, very important, extensive set of results on distributed algorithms for graph spanners that are not the greedy spanner. There are other constructions, other spanners. And you kind of show that these have all the nice properties and sometimes even better than what the greedy spanner has. But I'm going to give you 2 variants where we don't know those things, right? All the known distributed algorithms don't seem to give these variants that I care about, right, that I'm going to talk about. And the greedy spanner does, but we have no idea how to do that distributed. So, what do we do? Okay, so part 1 of this talk is kind of going over this greedy algorithm and talking about greedy spanners. Part 2, I'm going to talk about the LP norm objective. So this is a setting where it's going to be the same definition of spanner, so the definition is the same. But instead of kind of caring about number of edges, I'm going to care about the degree distribution in some way that I'm going to define. And then part 3, I'm going to talk about fault tolerant spanners, right? So now we're going to change the spanner requirement to have something to do with fault tolerance, which of course makes total sense in distributed computation and is of interest to many people here. But now I'm going to go back to caring about sparsity. But like I said, both of these are similar in that it's the greedy algorithm is the way we know to build these things. And I don't know any distributed way of doing it. Okay, so let's talk about the greedy algorithms. So I like to present this as kind of theorem 0 of spanners. You can see it's not the first paper. It's not from the late 80s. It's from the early 90s. But this is kind of like the result on spanners, right? Like all of the earlier stuff is awesome and led to the development of the field. But this was kind of the culmination of 5-6 years of hard work. So this theorem says that for any positive integer k, all graphs have a 2k minus 1 spanner, so an odd stretch, 2k minus 1, with n to the 1 plus 1 over k edges. And that's tight. There exist graphs where all the 2k minus 1 spanners have that many edges, assuming something called the Erdős-Grit conjecture. So I'm not going to go into the Erdős-Grit conjecture. I used to say that this was kind of uncontroversial, but I found out that that's false. I now have co-authors who don't believe in the Grit conjecture. So, okay, maybe you believe it, maybe you don't. But at least if you don't think that you can solve this old conjecture one way or the other, then this is kind of the right bound to be looking at. Okay, good. You can kind of note that this upper bound is just an existential statement. It says all graphs have these spanners. It doesn't say anything about computing. It turns out that even the original proof of this, despite being stated in this existential way, is algorithmic. That's the greedy algorithm. Right? The greedy algorithm is the first algorithm that we knew that gave these optimal spanners. Okay, so what is the greedy algorithm? It's kind of the obvious generalization of Kruskal's MST algorithm. Right? So in Kruskal's MST algorithm, right, I start with an empty graph. I look through the edges in non-decreasing weight order, and I add an edge if it doesn't cause a cycle. Right? So now all I'm going to do is I'm going to add an edge if I need to. I'm going to add an edge if the current spanner doesn't have stretch 2k minus 1 on this edge that I'm considering. Right? So if the current distance is bigger than 2k minus 1 times the weight of the edge, then I have to add the edge. And so I do. Okay, so very simple construction. Very easy to see that this does give me a spanner. Right? Any edge that I add, obviously, is good. Any edge that I don't add, because I didn't add it, its distance is preserved up to a factor 2k minus 1. So, okay, very simple. So one note, which is useful later, particularly when talking about fault-tolerant spanners, if my graph is unweighted, which is a particularly important setting, is a very important setting, then non-decreasing order just means any order. So you can use any order you want, and this thing will work. Okay, so to see an example, and again, this was a great collaborator of mine, Caleb Robel, who made this slide, these examples. Right, so I'm considering this edge. Maybe that's the first one in my order. Let's say this example is unweighted, and I'm at stretch 3, so k equals 2. And so I have some arbitrary order of the edges, and let's see what happens. Right, so I consider this v1, v2 edge. Current distance is infinity, so I definitely have to add it. Then this v1, v3 edge. Current distance is infinity, so I definitely need to add it. Then this v3, v4 edge. Current distance is infinity, definitely need to add it. Now I have this v2, v4 edge. You can see that the current distance is 3. Right? So I don't need to add this edge. And so I don't. Then I look at this v2, v3 edge, and I say the current distance is 2. So I don't need to add this edge, and so I don't. And I'm left with this as my spanner. Right? So in fact, in this example, it's the exact same thing as Kruskal's algorithm, because this is such a small example. Good. Okay, so good, so that's the greedy algorithm. Like I said, greedy algorithm has all these nice properties. I'm not even gonna scratch the surface. I'm just gonna give you a couple nice things. So one is that it has at most n to the 1 plus 1 over k edges. So that's proved by Theorem 0 by Althofer et al. And I'm not gonna actually use this, but I'm gonna throw it out there because it's one of the coolest results that I think I can remember seeing on spanners. Is a result by Filter and Solomon, which says that it's optimal also for weight. So the sum of the edge weights. So we're not talking about that. I'm talking about sparsity for now, as we're going to see. But if you care about something like the sum of the edge weights, like you would in MST, then this is actually the right thing to be doing in a very strong sense. And you should all go read this Filter and Solomon paper from PODC 2016 that says it's optimal. It's a really cool paper. It's one of these like really slick proofs, right? The main proof they have is like, half a page long, but it's just kind of very, very slick and very, very cool. Okay, a bunch of other nice results in a variety of contexts. In geometric spanners, if I care about other objectives, in doubling dimensions, in whatever. Greedy spanners are awesome. Obviously, in centralized land, they're kind of pretty efficiently computable. Right? I mean, certainly Polytime computable. If you kind of think about it for a minute, the obvious running time looks like m times n to the 1 plus 1 over k, right? Because to determine that stretch condition, I run an O of m time algorithm like Dijkstra in a graph of size like n to the 1 plus 1 over k, right? The size of my spanner. You can do some work and get this down to n to the 2 plus 1 over k. So Rodity and Zwick did this back in 2011. So that's strictly better. At least it's good. And actually, I'm not going to mention it, but we're going to use some of those same similar ideas from Rodity and Zwick when we do fault-tolerant spanners. spanners to make those faster also, which is kind of cool. Okay, so awesome. So greedy spanners are awesome in centralized land, but kind of rough in distributed land, right? It turns out in the local model, you can do this because these things do have locality. So all you need is some kind of standard graph decomposition. You lose an extra log n factor, no big deal. Except, once I lose log n's, I'm not optimal, right? Like, sure, I care about log n's less than I care about polynomials, but I do care about them, right? I have lost optimality in the size. So that's not good. And in the congest, I mean, who knows? Maybe someone here knows, maybe I'm missing some results, which is totally plausible. But I don't see any way, and I don't know any results that say that I can compute the greedy spanner or anything even like it in the congest model. Okay. Because of that, there's been a whole bunch of other papers that say, hey, let's build other spanners in congest or in local. So kind of I've mentioned two here, but there's a whole bunch. But these are kind of the two that I think are maybe the most central or most important. Botswana-Sen and Durble-Gavois, Peleg, and Viano. So a bunch of nice algorithms. So these are very nice algorithms. I'm not going to talk about them. You should go read them. They do some nice clustering stuff, some pathfinding stuff, some cool ideas. But they're not the greedy algorithm. They're building something else. That something else is a good spanner, right? They get very good size, some, other nice things, but it's not the greedy spanner. Okay, good. So that's part one of the talk. That's the setup. Let me talk about this first setting where we've done what I think is some cool stuff in the centralized setting that I don't know how to port over to the distributed world. Okay, so these are these two papers from iCalc and Approx last year. They have very similar names, norms of graph spanners and approximating the norms of graph spanners, with the same people. So this is with Edin Klomtach and Thomas Robinson. So Edin's a faculty member at Ben Gurion University at the Negev, and Thomas is his postdoc. And I think Thomas is probably on the job market this year, so you should consider talking with him. Good. So I'm really only going to talk about the first paper. The second one here is some approximation algorithms, which is a bit outside the scope of this talk. In fact, the second paper is like highly technical, and we get some results that are kind of very difficult to get that aren't mind-blowingly good. So I'm not going to talk about it too much. First paper is also super technical, very hard, but at least I can present some simple thing from it and give you the idea. Okay, so let's live in the unweighted setting. Very important setting for now. I want a 2K minus 1 spanner. Okay, but like what do I want else from it, right? Like if all I said was I want a 2K minus 1 spanner, I say use G, okay? Just use the original graph, that's a 1 spanner. As I've kind of alluded to, the kind of classical thing is the number of edges, right? This is what that theorem 0 talks about, right? Saying that I have n to the 1 plus 1 over k edges. So if I care about sparsity, this is nice, right? I have this, it's this very natural objective. There's this kind of beautiful theorem 0 of Althoff et al. Super well studied, often was needed in applications. But it has some drawbacks, right? So, and this becomes particularly apparent when you think in distributed world, right? That this doesn't really take into account degrees, right? Like you can imagine two spanners of the same graph, one which have the exact same number of edges, but one which is very kind of spread out, and one which is like has these nodes of super high degree. And they're both the same stretch spanners of the same graph, right? But one of them, seems worse, right? If I've got that node of high degree, then from a distributed setting, that sucks, right? Like that node has to handle lots of messages if I'm using this as an overlay or something like that. It's got high load, it has to keep track of more state. High degree is bad in distributed settings. And so, a standard place where we use spanners in theoretical networking or theoretical distributed computing is as an overlay. But, you might also want to use it as a physical thing, in which case, clearly, I can't have super high degree switches, something like that. And even as an overlay, like handling high degree is very difficult. So because of that, like another classical goal is to say, hey, I don't care about the number of edges so much. What I care about is minimizing the max degree, right? I want spanners where the max degree is very small. Okay, like that's a nice thing. You can look at it. It encourages this low load. That's nice, very natural setting. Of course, it has this kind of massive drawback that you can't get those same nice trade-off theorems like theorem 0. Right? So this is like super easy to see via something like the star. Right? So if I have the star, right, you take away any edge and it's no longer a spanner. Right? You take away any edge and some distance goes from 1 to infinity. So the only spanner of the star is itself. And the max degree there is n minus 1. Okay, so you can't kind of say, oh, I'm going to have higher stretch but get smaller max degree. Like you just can't do it. Another maybe more slightly subtle problem, but also very important, is that this is a very global notion, right? Like, okay, maybe I don't have the star, right? Maybe I get lucky and for the setting I'm in, there is ways of getting the max degree small. But even so, like maybe I can get the max degree small, but only somewhat small. And that's because kind of over here in my graph, like the max degree has to be relatively big for some reason. Whereas over here, the max degree could be very small. But if all I care about is minimizing the max degree, I'm going to say, oh, the max degree has to be relatively big because of this stuff. So over here, just do something dumb, make the max degree the same as it is over there. Like, there's no reason for you to do well in that part of the graph where you could do well. Right? Unlike sparsity, right? Sparsity is, everywhere that you can make progress, you're going to be able to make progress in some sense. So that's a problem, right? Like the fact that one little part of my graph can force this kind of the graph as a whole to say that no, that you just can't have these good things is not great. So what I want is something that interpolates between these two. Okay, so I want the max degree to be small. I want some objective that encourages the max degree to be small. But I also want to say that, hey, if this node has to have large max degree, I don't want to just give up everywhere else. Right? I still want the other nodes, if they can decrease their degree, to do that, to have small degree. Okay, so I claim there's an obvious way of doing that, right? And that's by looking at this degree vector. Okay, so I say, look at my graph, look at the vector of degrees. The number of edges is just half the L1 norm, right? The L1 norm is I sum up the absolute values. In this case, they're all non-negative, so I just sum up the entries. And then I divide by 2, except double count at every edge. And the maximum degree is the infinity norm. Right? Infinity norm is the max entry, that's the max degree. And of course, like there's an obvious way when phrased in this language to interpolate between these two, right? It's to use the P norm. Right? So the LP norm, the objective is to find the spanner H, or define a spanner H, which has small P norm. What that means is P norm of its degree vector, right? Which means that I look at this degree vector, I raise every entry to the P, I sum those all up, and then I take 1 over P. Okay, so this is the P norm. So for the 1 norm, this is the number of edges. For the infinity norm, this is the max degree. Take the limit appropriately. And for stuff in between, it kind of encourages both sparsity and low max degree. I'm using encourages here in a slightly vague way, but you can kind of convince yourself, hopefully. Okay. And because of that, looking at the P norm of some vector is a totally standard thing to do in clustering and scheduling. You see this in machine learning a lot, but particularly in clustering, right? This is like k-means. Looking at P norms matters, right? Because L1 norm has some bad things, L infinity norm has some bad things. L2 or LP in general is some nice interpolation between the two. Right? And for some reason, even though this is this totally standard thing in these other settings, hasn't really been looked at here. So I'm saying, let's look at it here. Let's see what happens. Okay, so this is the main result. So we introduced this in our iCalc paper. And it says, it's an analog of the theorem 0. So I'm saying every graph admits a 2k-1 spanner with LP norm. Now this is a little more complicated, right? It's not n to the 1 plus 1 over k. It's n max of n and n to the k plus p over kp. Okay. Good. So you can see when k is 1, that's 1 plus 1 over k. That's good. Good. And that's also tight, assuming the grid conjecture. Right. So again, as we're going to see, there's some graphs which I'm going to show you, which are this is maybe not the greatest theorem. Like this isn't super impressive in terms of the bounds, but it's the best we can hope for, assuming the correct conjecture. And there are some regimes where it says some very nice things. So another nice thing about it is that the algorithm is the greedy spanner, which means the greedy spanner takes k as a parameter, but certainly doesn't take p. Right. So actually, the same spanner is working simultaneously for all p. Okay, so that's kind of a cool fact. It's always nice when you get that. But again, like we're very strongly depending on this being the greedy spanner. I don't know how to prove that the Buzz-Wanna-Sen spanner has this property or something like this. Okay, so let's interpret this k plus p over kp. So to start out, let's just see the stretch 3 setting. Right, so we're going to build up from there. So for stretch 3, kind of the main lemma we prove is that for stretch 3, so k equals 2, and when p is 2, so the 2 norm, every graph has a spanner with 2 norm O of n. And that's tight because, again, the star proves that any LP norm is never going to be below n. Right, the star, any p norm of the star is theta of n. Right, so for these existential bounds, I'm not going to get below theta of n. That's why I have this max of n into the k plus p over kp. Good. So we're going to prove that the L2 norm for stretch 3 has an O of n norm span. Then we're going to say, okay, beyond that, that's the monotonicity of norms, right? If it's O of n 2 norm, then it's O of n p norm for any p at least 2, right? And p norms have this property. That's super easy. And then actually in between, we just have to use Holder's inequality. So I'm actually not going to do this. And in fact, it took us an embarrassingly long time to realize this. We had a whole kind of separate argument for every different value of p between 1 and 2. But you don't need to do that. All you need to do is prove this one bound, and then say that Holder's inequality gives you this interpolation between 1 and 2. And beyond 2, you monotonicity of norms, so you get exactly this result. And then you can do the same thing for stretch 5. So for stretch 5, what we're going to prove is that at the 3/2 norm, right? So when stretch 5 is when k equals 3, right? So in 3/2, that's when k plus p over kp is equal to 1. Good. So again, we're going to prove something special about the L3/2 norm for stretch 5, that it's always at most O of n, and then use monotonicity of norms and Holder's inequality to get the other two regimes. Same with stretch 7. Okay, et cetera, same for stretch 2k minus 1. Right, that's our strategy. If we find out where it's supposed to be O of n, we prove it there, and we use monotonicity of norms beyond that, and we use Holder's inequality between 1 and 3. Okay, so I'm going to try to convince you, I'm going to sketch out that special case of stretch 3. It turns out this is not so hard. The real difficulty is once you're at stretch 5 and beyond. But okay, let's try to do it for stretch 3. So, okay, sketch. So first, I claim that the contribution of nodes of degree at most 2 root n is small. Right? So nodes that have degree small below root n. Well, even if it's all of them, even if it's n, right, then their contribution to the 2 norm is at most, n times root n squared, all to the 1/2. So that's just O of n. Right, so nodes of degree less than root n don't affect my 2 norm very much. Okay, and the fact that H has girth at least 5 implies that any 2 vertices have at most 1 common neighbor. Okay, so here's a key fact about the greedy spanner that other spanner constructions don't have. Okay, the fact is that the greedy 2k minus 1 spanner has girth at least 2k plus 1. Okay, so remember that girth is the length of the smallest cycle. Right? So you can kind of immediately verify that the greedy spanner has that property. And other spanner constructions don't. Okay, in particular, a lot of distributed constructions don't. And I'm going to very much depend on having this property. That's how my analysis is going to go. Right, so I'm going to say H has girth at least 5. So any 2 vertices have at most 1 common neighbor. Otherwise, it would be a cycle of length 4. And that lets me kind of very easily claim that for any degree bound D that's at least 2 root n, there's at most 2n over D vertices of degree at least. Okay, good. So how do I do that? Well, look at a high degree node. It's got at least D neighbors. Okay. Look at another high degree node. It's got at least D minus 1, like new neighbors. Right? Maybe one of its neighbors is overlapping with the previous node, but the rest are all kind of new, right? Because of the girth bound. Look at the next kind of high degree node. This has at least D minus 2 kind of new neighbors. Right? So every time I see, I can repeat this process, right? For the L high degree node, I see at least D minus L new neighbors. Okay? And I can only do that basically n over D times before I've just seen all the nodes. Right? So very easy calculation says that I can only do that, about n over D times before I've just used up all the nodes, right? My kind of these new neighbors that I'm seeing now add up to more than. Okay, so because of that, that means that the contribution of nodes of degree D, again, is 2n over D, because that's how many there are. D squared, because that's the degree squared, 1/2, so it's O of n. Okay, so that was just for the specific degree band, but now, of course, I can break into classes, right? My powers of 2, and then I'll lose an extra log n. Turns out it can be a little more clever and not lose that extra log n. I'm not going to go into the details. But fine, that's how it works, right? So high degree nodes contribute O of n, low degree nodes contribute O of n, the whole thing is O of n. So if I want to go to stretch 2k minus 1, the way I do this is I say, okay, the greedy spanner has girth at least 2k plus 1. Let me prove that any graph with that girth has this LP norm. Okay, so again, this works fine for the greedy spanner. This analysis doesn't work for most distributed or any distributed spanner construction that I know. Maybe someone here will crit and say there is one, and then that's awesome. Then we have this result, and I'm very happy. So the obvious approach here is to just go back to my previous thing, replace this 2 root n by 2n to the 1 over k. Unfortunately, if you try to do that, you get these theorems that are false, right? So I spent a lot of time trying to kind of push this through before I realized, like, it's not just that it's hard to push through, that approach doesn't work. The lemma that I need is false. So we have to do something kind of much more technical and much more difficult that I'm definitely not going to go into the details of. And I'll say Thomas Robinson, the postdoc on this, did a lot, the vast majority of that work. So kudos to him. Yeah, so that's a very complicated thing. Go look at our paper. It's cool, but it's very complicated. I don't know how to do this in distributed language, right? If I want to go through the same analytic process, I need some distributed spanner construction that has large girth. I don't know of any. Even computing the girth in distributed settings is kind of hard. There's a bunch of interesting papers on that. You Google them. Another way of doing this would be to try to use some different analysis, right? Do something totally different. Don't depend on the girth. Just argue directly. Right? The same way that for sparsity, theorem 0 actually also uses the girth of the greedy conjecture. Whereas like Baswana-Sen and Durable et al., like those papers don't use the girth, right? They analyze size in a different way. So maybe there's some other analysis of those that says they also have good P norm. That would be cool. I don't know how to do it, but maybe someone here does. I hope you do. And please let me know. Okay, so in the remaining 20 minutes-ish, I want to talk about fault tolerance spanners. So here it's really these 4 papers, but I'm really going to focus pretty much exclusively on this top one. But I'll talk about the others in terms of the history. The top one was just accepted at SOTA, which is very cool. So this is with a whole bunch of people, or in general, right? So you can see Greg has been on a bunch of 2 of these papers with me. Caleb Robel. So I'll mention Caleb is an undergrad from the University of Maryland, Baltimore County, who is applying to grad school this year. So if he applies to your school, you should accept him. He already has a SOTA and a PODC paper. He's awesome. And then a paper from 2018, also with Greg, but with also Marav and Virginia. And then a much older paper from back when I was a postdoc in 2011 with Roby Kratramano. And you can see there's some trends here, right? Like simple, optimal. Okay, Good. So let's talk about fault tolerance spanners. So switching gears now, not talking about the LP norm anymore. Let's go back to number of edges. And if what I care about is number of edges, and I'm again centralized, then in theory we're done, right? This theorem 0, the greedy algorithm is great. It gives us the right bound. We know everything. Good. Okay. In practice, in particular in distributed systems, things can go wrong. Right, so let's look at this nice picture that Greg made up. Look at this gray graph. Let's say I want to build a 3-spanner of that. Okay, maybe you run the greedy algorithm, and you get back this red graph. That's a 3-spanner. Everything's good. Happy with this. Right? But now, of course, because I'm in distributed land, I have faults. Right? So in particular here, suppose that this node breaks. The node goes down. This is very bad news, right? This disconnects my spanner. And it's kind of particularly heartbreaking, right? Because the underlying graph is still connected. Like maybe fine, like I disconnect, the graph gets disconnected, but maybe that's kind of inevitable. But here it's like not inevitable, right? It's because I'm using the wrong spanner. If I was using if I was using this edge, I would be much happier with it. Okay, so I want to handle faults. So here's the following definition. I should give credit where credit is due, actually. This is due to Chechik, Langberg, Peleg, and Rodity in 09, I believe, building off some previous stuff in geometric land. So they say that a subgraph H is an F vertex fault tolerant 2K minus 1 spanner. If for every set of faults, of at most F faults, sorry, what remains of the spanner, H minus F, is still a spanner, stretch 2K minus 1, of what remains of the graph, G minus F. Okay, so in some sense, this is an obvious definition, but it's surprisingly subtle, actually. Right, so for example, as you can see, H only has to be fault tolerant if G is fault tolerant, right? Like if G minus F is disconnected, then of course H minus F is going to be disconnected, right? There's nothing I can do about that. So this means, for example, that like if G is some totally crappy graph, right? If G is a tree, which is not in any kind of notion of the word fault tolerant, right? Well, if H is just also that tree, then H is kind of N fault tolerant. H is maximal fault tolerant because it just has the exact same behavior as G. So it's a little bit weird, but it's kind of the obvious definition. And the natural question here is like, how much do I need to pay for fault tolerance? Right? Like I have to pay n to the 1 plus 1 over k edges just to be a 2k minus 1 spanner, right? The Erdős-Group conjecture tells me this. How much more do I need to get F vertex fault tolerance? Right? So there's a very reasonable intuition, right? Which is building off of, let's say, fault tolerance in normal graphs, not in spanners. Right? So if I don't have distance preservation, so I'm not spanners, if I just want to be an F-connected graph, right? You're F vertex connected. It's long been known, basically from Menger's theorem, right? That F vertex connected graphs need Fn edges, right? Whereas just to be, one connected, I only need O of n edges, right? Any tree. So I'm paying an extra factor of that. And that's very reasonable intuition, right? Like if I want to be F robust, I kind of need F copies of this thing that's not robust. Right? So in 2018, we proved a lower bound that didn't quite reach this F. We got F to the 1 minus 1 over k as the extra cost. Okay, so good. So for a long time, I certainly believed in this F lower bound, and the original kind of results were kind of basically trying to reach that. Right, so this first result of Chechik, Langberg, Peleg, and Rodity, this is 2010, this is the journal version. This paid an extra factor of kind of k to the f, okay, so exponential enough. And you can kind of think like k is maybe some constant, right? I mean, my stretch somewhere between constant and log n. F, somewhere between constant and like n, right? I might want to handle very large values of fault tolerance, right? Like root n fault tolerance is absolutely something I might be looking for. Okay, so then in 2011, that paper with Roby that I mentioned, we got this down to f to the 2 minus 1 over k. So that's good. It's polynomial in f. And we also got the runtime down. So note that the original runtime was k to the f. So that's exponential if f is big. So we got that down to a polynomial, which we're very happy about. Then there are these two more results, like 7 years later. So it's kind of a stagnant for a while. Then we kind of proved some cool stuff. So this is our SOTA 2018 paper with Greg and Murab in Virginia. So we got this f to the 1 minus 1 over k. So we broke through this kind of f intuition and said you have to pay less than f, only f to the 1 minus 1 over k. And yeah, okay, exponential in k, but we can think of k being a constant, and then we're kind of okay. And then actually a year later, so at PodC 2019, there was a very nice paper by Greg and Patel, a undergrad from Georgia Tech, who said, actually, you don't need that exponential in k. It really is optimal. It's f to the 1 minus 1 over k. Remember, we had that f to the 1 minus 1 over k lower bound. So this is optimal size. Running time is actually, this is the greedy span. So what they proved is like the natural greedy algorithm, which I'll talk about in a minute, when you kind of change it to fault tolerance, gives you this cool thing. Okay, so then more recently, so these two papers, so this is in PodC this year, and this is in SOTA coming up. What we really wanted was Polytime Computation, right? So that's what this blue is. This is saying that these are in Polytime, and we went through a lot of work to actually make it as fast as we could, but the point is Polytime. In this first paper, we got almost optimal size. Again, there's not even exponential in k, just a linear in k extra factor. And then in this follow-up, we get it all the way down to like optimal size spanners in polynomial running time. And again, like there's a whole bunch of other stuff in these papers. Like this SOTA paper is not just shaving off a factor of k, it's doing other things. But this is the result I'm going to mostly talk about. Okay. So you can kind of see there's these like three waves. And because these are all the greedy spanner or some variation of it, don't know how to do it distributed. Of course, like fault tolerance, like distributed computation, like the distributed world is where we care about fault tolerance. If you're centralized, who cares? Right? But fault tolerance is a natural distributed notion, and yet the only algorithms we know to do these are very, very centralized. So this 2011 paper can be made distributed, and that's in that paper. But now that's no longer optimal size. Okay, so good. So what is the greedy fault tolerant spanner algorithm? It's like I said, we originally analyzed this in a SOTA 18 paper, and then Badr and Patel gave a much, much better analysis of it. Like much, much, much better analysis of it, like super simple compared to our crazy complicated analysis. That's the obvious thing, right? It's changing the greedy algorithm to say not just is the current distance bigger than 2k minus 1 times the weight, but is there a fault set that makes the distance bigger than 2k minus 1 times the weight? So let's see the example. And so again, like before, I consider this v2, v1 edge, got to add it. v1, v3 edge, got to add it. v3, v4 edge, got to add it. So now I have this v2, v4 edge. Right? Before I didn't need to add this, right? The stretch between v2 and v4 is only 3. But now if I fail v1 or v3, right? Suppose v1 or v3 like die. Then in the underlying graph, the distance between v2 and v4 will be 1, right? Because there's an edge there in the underlying graph. But if v1 and v3 fail, then in the spanner, my current spanner minus that fault, v2 and v4 are disconnected. So they have distance bigger than 2k minus 1 times the weight. So now the greedy algorithm has to actually add that edge. Because there is a fault set that forces the greedy algorithm to add it. Good. Now I look at this v2, v3 edge, and now I say, oh, no matter what fails, right? If v1 fails or if v4 fails, doesn't matter which one, there's still a length 2 path, right? So that's stretch at most 2, which is stretch at most 3. So now, no matter what fault set happens, as long as, again, f is 1 in this example, so any fault set is just either v1 or v4. Either way, I'm already happy, so I don't need to add this edge. Okay, so this is my spanner. Good. Right, so the main theorem of Bodwin and Patel is that this greedy spanner has f to the 1 minus 1 over k and to the 1 plus 1 over k edges. Awesome. But there's this problem, which is this if condition. Like, is there a fault set which causes this? It turns out to be an NP-hard problem. So that's not great. So if we want polytime computation, the main idea is to relax that greedy algorithms, right? To say, I can't solve this NP-hard problem, so I'm going to make mistakes. I can't make a mistake in one direction, right? If the greedy algorithm tells me to add an edge, like I better add it in order to have correctness. But if I don't add an edge I'm supposed to add, now I'm not even a spanner. Right? Forget the size, I'm just not even a fault-tolerant spanner. So any edge that the greedy algorithm wants me to add, I better add. But if I'm flexible in the other direction, right? Maybe there's edges that the greedy spanner doesn't want me to add. If I still add them, I'm okay. I'm still going to be a spanner. I just need some argument for why I don't add too many. Right? So I'm going to be flexible. I'm not going to solve that problem. I'm going to, intuitively give an approximation, although that's not actually what we're going to do. I'm going to be flexible to a relaxed greedy algorithm. Okay, so in our PodC paper, we gave an approximation algorithm. We just straight up approximated it. And it turns out when you carry through the Bodwin-Patel analysis with now having an approximation algorithm, you lose that extra approximation factor, in this case, k, in the size. So that was the main idea. Again, there's more stuff in that paper. It wasn't quite that simple, but that was the main thing. In our new paper, we kind of bypass this. We don't approximate it. We do some other things, which I'm going to try to talk about, but I'm kind of out of time, so I'll just go through very fast. So the main idea there is to kind of really utilize random sampling. So again, not going into details, but it turns out the Bodwin-Patel analysis of the greedy algorithm, the way it works is it says, let me look at a random subgraph. Okay? That random subgraph might have some cycles in it, but based on the way that the greedy algorithm works, you can prove that it's kind of close to a graph that has no cycles. Right? So I sample this subgraph. There might still be cycles left, but because of how the algorithm works, I can remove some extra edges. And now what I'm left is no small cycles, no cycles of like 2K or less. So now I've got large girth. That means that there can't be many edges. Okay. Now, because my subsampling wasn't too harsh, because I didn't get rid of too much stuff, I can't have started out with too many edges. That's how the Bodwin-Patel analysis works. And we're going to kind of take that analysis and just like shove it inside the algorithm. Right? That's the main idea here is I take that previous analysis and I put actually the analysis inside the algorithm, right? Which kind of backwards from what we usually do, right? Usually you look at the algorithm, then do the analysis. We look at the analysis, put it in the algorithm. Right? So our algorithm samples a bunch of subgraphs. As to do that, you include every node with probability like 1 over f, actually 1 over 2f. Do that a whole bunch of times, like log n times. Say, hey, let's assume that, let's just go back to the old school theorem 0 greedy algorithm. Say, hey, I'm trying to add UV. On each of these subgraphs, would the greedy algorithm, the old greedy algorithm, add this edge? If there's a reasonable fraction of the subgraphs that say, yes, the greedy algorithm would add that edge, then I'm going to add it. And otherwise, I'm not. Okay, so very simple algorithm. The analysis and the correctness, what you kind of have to argue is that, if the greedy algorithm would have added it, then I add it. So you say, okay, if there is a bad fault set F, then when I do this random sampling, you do out the math, it turns out that in a large fraction of my subgraphs, with very high probability, it's going to look like I need to add the edge. Like all of F gets killed, so I need to add the edge. Fine, so I'm going to add it, so my algorithm is correct. For the size, so I'm basically out of time, so I'm not going to really do the size, but it's doing the Bodwin-Patel analysis again, but now it's saying that cleanup step, where it said based on the algorithm, there's some way of destroying all the remaining small cycles. No, I mean, my algorithm just kind of said, right, like if I add an edge, that means that in kind of most of these subgraphs, a lot of the subgraphs, it's not closing off a small cycle. So great. Now I can just use that. It's all very simple and direct. This is again like a surprisingly short proof. So like I said, in that paper, we do a lot of stuff. We do some very complicated things, but this main thing, like a one-page proof. So I'm not going to do the details. Good, but basically you say that without doing the details, you say, hey, I can find this H double prime, which is a cleaned up version of one of these random subgraphs, right? So H prime is one of these random subgraphs. H double prime I've cleaned up to get rid of all small cycles. Because it has large girth, it has few edges. On the other hand, because of how the algorithm works, I didn't have to remove too much in the cleaning step. So that means that, my size of this H double prime is like 1 over f squared, right? Because I sample every node for probability 1 over f. So it's like 1 over f squared of what I started out with. Now I just, use those two inequalities, this inequality and this inequality, and out pops the bound I'm looking for. Okay, so very nice. Right, so to summarize, there's a lot more in all of these papers, so you should go read them. But the point for this audience and for this talk is that we know these efficient polytime algorithms for size optimal vertex fault tolerant spanners. Okay? But the only way we know to actually get this optimal size spanner is through some variation of the greedy algorithm. Like I said, this old paper can be made distributed, but now it's not. So, I don't know how to make this distributed. And of course, I care about fault tolerant spanners most when I'm distributed. So yeah, I don't know. This is a great question. Maybe, here I have this notion of a relaxed version of greedy. Maybe there's some notion of relaxation you can use to actually do some version of relaxed greedy in a distributed way. That would be super cool. I'd be very excited. Maybe you can adapt Boswell-Sen or Durable et al. Or any of the other, your favorite distributed spanner algorithm. Maybe there's some way of adapting that to be fault tolerant. Maybe. That would be also very cool. I don't know how to do it. Like we very, very strongly depend on these greedy properties, but that'd be cool. Okay, right. So to conclude the whole talk, right, we have these two different settings, LP norm spanners and fault tolerant spanners. I've seen kind of a bunch of recent progress, particularly fault tolerant spanners, but also LP norm spanners in the last couple of years, both of which make more sense in distributed or network settings than they do in centralized settings. And yet we don't know distributed algorithms for them. So this is my challenge to you, the distributed graph algorithms community, and me, because I'm also in this community, but can we design good distributed algorithms for these spanner variants? I imagine the answer has to be yes, but I don't know. I think it's a really exciting direction. So if you're interested, shoot me an email, contact me on Zulip, come chat. I'd love to talk about these with people who know more about distributed graph algorithms than I do. Okay, thanks. And thanks to all my co-authors, especially. But thanks to you, the audience. And thanks to the organizers for inviting me. Cool.